Minimum weight spanning trees, Kruskal's greedy algorithm. Let us return to the applications of trees. If G is a connected graph, we say that T is a spanning tree of G if G and T have the same vertex set, and each edge of T is also an edge of G. Clearly, any connected graph G will have at least one spanning tree. Indeed, if G is a tree, then it is its own spanning tree. If not, then it is not a minimal connected graph. So we can omit an edge from it so that we get a connected graph G prime. If G prime is still not a tree, then we can continue the same procedure. We will only have to stop when we get a minimally connected graph that is a tree. In general, a connected graph will have many spanning trees. Theorem 10.7 shows, for example, that Kn has n to the n minus 2 spanning trees. Sometimes it can be quite difficult to find the number of all spanning trees of a connected graph. Spanning trees have a plethora of practical applications, especially in graphs with weighted edges. A classic example is the following. A railroad wants to expand into a 20-city area where presently they have no lines. They thoroughly analyzed the relevant data, and for each of the 20 choose 2, which is equals to 190 pairs of cities they know, the exact amount they would have to spend to build a direct link between those two cities. The railroad wants to build a connected network. That is, every city should be reachable from every city, but they want no redundant lines. How can they find the cheapest possible network? A graph theoretical description of this problem is the following. Example 10.10. Let G be a connected simple graph, and let W, which maps from E of G to R plus, be a function. Find the spanning tree T of G so that the summations of W of E, summing for all E in T, is minimal. The function W is usually called the weight function or cost function of G, and the W of E is called the weight or cost of E, while the summations of W of E, summing for all E which is in T, is called the weight of T. It is a common practice to write the weights of the edges on the edges as shown in figure 10.5. If G has only a few edges, then we might try to find its minimum weight spanning tree by examining all spanning trees. For only slightly larger graphs, however, this approach would take too long. Indeed, if n is equals to 20 and G is equals to Kn, as in the railroad example, then we would have to compute the total weight of 20 to the 18, which is greater than 2.5 times 10 to the 23 spanning trees. If our computer could handle 1 billion spanning trees per second, it would still need 2.5 times 10 to the 14 seconds, or more than 91 years to do it. Therefore, the quest for a general method to find the minimum weight spanning tree is undoubtedly well motivated. How would we start building up such a tree T? One can try the greedy way. That is, take the edge with the smallest weight or one of the edges with the smallest weight, if there are several, and put it in T. Second, look for the edge that has the smallest weight among those not in T, and add it to T. In the third step and all subsequent steps, we must be a little more careful. We have to make sure that by adding the new edge, we will not create a cycle. In general, in the ith step of this greedy algorithm, we look for the edge EI that has the following properties. 1. The edge EI is not yet in T. And 2. If we add EI to T, the obtained graph does not contain a cycle. And 3. The weight of EI is minimal among all edges that have properties 1 and 2. When we found this edge EI, we add it to T. It is clear that we can continue this procedure until T has n-1 edges, as a graph on n vertices and less than n-1 edges cannot be connected. However, G is connected, so if T has less than n-2 edges, we can find an edge of G that lies between two connected components of T and can therefore be added to T. The alert reader could note that the graph T that we obtain this way after I steps is not necessarily connected. All we know is that T is a cycle-free graph, that is a forest. However, if we continue this algorithm up to step n-1, then T will be a forest with n-1 edges, that is a tree. Will the greedy algorithm give us the minimal weight spanning tree? The answer to this question is not obvious. There are problems for which the greedy algorithm does give the good answer, such as finding the three-element subset with the largest sum in any finite set of integers. There are also problems, however, for which the greedy algorithm does not give the correct answer because greedy steps at the beginning adversely influences our choices later. An example for this is finding two vertex disjoint edges with minima total weight in the graph shown in figure 10.6. Here, the greedy algorithm results in a pair of disjoint edges with a total weight 11. So the correct answer is clearly 4. This problem, called the minimal weight matching problem, is another very important problem. We will learn about matchings in the next chapter. For the task at hand, however, that is for finding a minimal weight spanning tree, the greedy algorithm works. To prove this, we will need the following interesting property of forests. Lemma 10.11. Let f and f prime be two forests on the same vertex set V, and let f have less edges than f prime. Then f prime has an edge E that can be added to f so that the obtained graph F union E is still a forest. Proof. Assume that there is no such an edge E in f prime. Then adding any edge of f prime to f would create a cycle in f. So all edges of f prime are between two vertices of the same component of f. Therefore, f prime has at least as many components as f. This is a contradiction. However, as we know that a forest on n vertices and with k components has n minus k edges, so if f prime has more edges than f, it must have less components. Now we are in a position to prove the main result of this section. Theorem 10.12. The greedy algorithm always finds the minimal weight spanning tree. Proof. Again, we use an indirect argument. Assume the greedy algorithm gives us the spanning tree T, whereas our graph G has a spanning tree H, whose total weight is less than that of T. Let H1, H2, H3, and so on to Hn minus 1 be the edges of H so that the weight of H1 is less than equal to the weight of H2 and so on, which is less than equal to the weight of Hn minus 1 holds. Similarly, let T1, T2, T3 until Tn minus 1 be the edges of T so that the weight of T1, which is less than equal to weight of T2, and so on, which is less than equals to the weight of Tn minus 1 holds. Let I be the step at which H first beats T, that is, let I be the smallest integer, so that the summations of W of Hj, summing starting with the j equals to 1 until j equals to I, which is less than the summations of W of Tj, summing with j starting from 1 to I. Such an index I exists as at the end H beats T, so there had to be a time H took the lead. It is also clear that I is greater than 1. as W of T1 is the minimal among all the H weights of G, as I is the first index at which H took the lead. The inequality W of Hi, which is less than equals to, which is less than W of Ti, must hold. Indeed, this is the only way. That is, the summations of the weight of Hj, summing with j starting from 1 to I, which is less than the summation of W of Tj, summing with j starting from 1 to I, and the summations of W of Hj, summing with j starting from 1 to I minus 1, is greater than or equals to the summations of weight of Tj, summing with j starting from 1 to I minus 1, can both hold. We will deduce a contradiction from this, that is, we will prove that with W of Hi, which is less than W of Ti holding, the greedy algorithm could not possibly choose Ti at step I. Let Ti minus 1 be the first the greedy algorithm produced in I minus 1 steps. That is the union of the edges T1, T2, T3 until Ti minus 1, and let Hi be the first formed by the edges H1, H2, H3, and so on until Hi. Applying lemma 10.11 in Ti minus 1 and Hi, we see that there is an edge Hj for some j which is less than or equals to I that can be added to Ti minus 1 without forming a cycle. However, our definitions show that Hj, which is less than or equals to Hi, which is less than Ti, so at step I, the greedy algorithm could not add Ti to Ti minus 1, as Ti did not have minimum weight among the edges that could be added to Ti minus 1 without forming a cycle. This proves by contradiction that no spanning tree H can have a smaller total weight than T, the tree obtained by the greedy algorithm. We would like to point out that there are several ways to attack the problem of finding a minimal weight spanning tree with a greedy algorithm. We could, for instance, insist on keeping the graph we are building connected in each step. The particular algorithm we covered in this section is called Kruskal's algorithm, or the Kruskal algorithm, namely after his inventor, the American mathematician Joseph Kruskal.